SwayamPrabha. Digital India. Educated India.
Good morning. Now we will start discussion on a new module, tutorial on incineration. In the previous module we have discussed different aspects of incineration and waste to energy conversion. In this module we will solve some numerical problems on incineration. The first problem is a dry MSW has the following composition on mass basis: carbon 40%, hydrogen 5%, oxygen 30% and ash 25%. Determine the stoichiometric oxygen requirement for the combustion of the MSW. Assume the ash as inert and average molecular weight of ash is 56. If the ratio of nitrogen to oxygen in air is 4:1 volume by volume ratio, determine the stoichiometric requirement of air. So, this is the problem statement. We have to determine the stoichiometric requirement of air and we have to also determine the stoichiometric oxygen requirement. So, to solve this problem we have to take some basis. So, our basis here say 100 gram of dry MSW. So, we will try to understand out of this 100 gram how many gram of carbon, hydrogen, oxygen and ash are present. Then we will convert it into moles to get the molecular formula of the waste. So, carbon is say 40 gram, 40%, it is here 40%. So, out of 100 it will be 40 gram, hydrogen out of 100 will be 5 gram and oxygen out of 100 gram will be 30 gram. So, remaining 25 gram is ash as per the statement. Now, if we want to convert this gram into moles, we will divide it by the molecular weight of carbon, that is 12. So, 40 by 12, that is equal to 3.33 moles for carbon. For hydrogen this is 5 divided by 1, that is equal to 5 moles, and for oxygen 30 divided by 16, so 1.875 moles. For ash it is 25 divided by 56, so that is equal to 0.4464 moles. So, on the basis of these moles which is present in 100 gram of dry MSW, so we can represent this biomass in terms of this C 3.33, hydrogen 5, oxygen 1.875, it is coming from this 1.875 and ash is equal to 0.4464. So, this is the molecular formula of the MSW, we can represent in this way. Then what we need to do? We have to calculate the oxygen requirement and air requirement. So, this is the representation of the MSW, the Ca, Hb, Oc and Sg. So, this is reacting with say d mole of oxygen and it is giving us E mole of H2O, F mole of CO2 plus G mole of ash. Here we do not have any sulfur, nitrogen or chloride, therefore, those elements will not be present in the product. So, here basically the MSW is composed of carbon, hydrogen and oxygen and ash. So, the products will also contain CO2 and H2O basically and rest will be the ash. So, this is the representation of the reactions, the combustion reactions. Now, we have to get the value of D. So, this is 1 mole is reacting with d moles of oxygen. So, molecular stoichiometric requirement of oxygen is D with 1 mole of this material, or we can say also for 100 gram of the MSW. So, if we can find out the value of D, then we can get how much oxygen is required for the stoichiometric combustion of this MSW, which is represented by C 3.33 H5O 1.875 and S 0.4464, and this is the reactions. Now you see, if we do the balance, so by these reactions and which is given here, so see 3.33 moles of carbon is present, so this Ca. So in these reactions, if we consider this is our biomass, this is our waste MSW, it has 3.33 of carbon. So A is equal to 3.33, then B is equal to, we are having 5. So B is equal to 5 and C is equal to 1.875 we are getting. So as G of S is here, this will be inert. So this is not reacting. So the amount of S here in G mole of S will be available here at G mole of S. Now we will be going for component balance and we will find out the value of D. So how this can be done? So this is our reactions, we are ignoring the S, this is inert and this is our molecular formula, molecular presentation of this MSW. So for carbon balance Ca, that is A is equal to F, A is equal to F. So left hand side of this reaction or equation we are getting A moles of carbon, right hand side we are getting F mole of carbon. So A is equal to F, and B for hydrogen balance, B is equal to, we are getting 2 into E. So B is equal to 2 into E, and for oxygen balance C moles and plus 2 into D, C plus 2 into D in the left hand side, and in the right hand side we are getting E plus 2F. So E plus 2F, so oxygen balance, there is a balance of the components. So A is equal to F equal to 3.33, we have got 3.33 A equal to, B equal to 5, so here B equal to 5 and B equal to 2E, so E is equal to B by 2, so E is equal to B by 2, 5 by 2 is equal to 2.5 and C is equal to, already we have got 1.875, and from this expression C plus 2D is equal to E plus 2F. If we replace the values of this C, E and F, we can get the value of D. So that has been done here. So C is 1.875 plus 2D, that is equal to E 2.5, just we have calculated D is equal to 2.5. So we put the value of 2.5 here and plus 2 into F, so 2 into F. So value of F equal to A equal to 3.33 we have got. So we will multiply this 2 with 3.33. So this is the expression through which we will get the value of D, or by rearranging we are getting 2D equal to 2.5 plus 2 into 3.33, that is 6.66 minus 1.875. So that is equal to 7.285. So that is equal to 2D. So D will be 7.285 divided by 2, that is equal to 3.6425. So this is our D moles, moles of oxygen which is reacting with this MSW. So this is the D we are getting now. Then what is the stoichiometric requirement of oxygen now? So therefore 100 gram of MSW, oxygen requirement will be this moles of 3.6425 into O2. So O2 is equal to 32, that is we need here D moles of O2 and D value we are getting 3.6425, 3.6425, and then molecular weight of oxygen, molecular weight of oxygen. So here we have to put this is equal to 32, not 16. If only O, then it would be 16, but it is here O2 as per the expression DO2. So that is why how much oxygen is required? 3.6425 moles multiplied by 32. So 116.56 gram. So 116.56 gram of oxygen is required. So this is the stoichiometric requirement of oxygen, 116.56 gram per 100 gram of MSW, or 1.1656 gram oxygen per gram of MSW. So this is the first part of the problem. that determine the stoichiometric oxygen requirement for the combustion of the MSW. Now, second we have to calculate the requirement of air. It is also given that nitrogen to oxygen in the air is 4:1 volume by volume ratio. So, we will consider this information here. So, nitrogen in the air will be how much? 4 of this, 4 of 3.26425. So, 4 into 3.6425, that is equal to 14.57 mole. So, this is nitrogen present in it as per the statement. So, mass of nitrogen will be how much? Molecular weight of nitrogen. So, 14.57 into 28. So, then we are getting 407.96 gram. So, this gram of nitrogen and this gram of oxygen is required. So, what is the total mass of this? So, total mass of air, that is equal to 407.96 plus 116.56, that is equal to 524.52 gram. So, now stoichiometric requirement of air is equal to 524.52 gram air per 100 gram of MSW. So, this is the second part of the problem. Now, we will come to our second problem. So, the statement of the second problem is a MSW has the following composition on mass basis: carbon 35.5%, hydrogen 4.8%, oxygen 25%, nitrogen 0.40%, sulfur 0.15%, chloride 0.55%, moisture 26% and ash 7.6%. Assume average molecular weight of ash is 56. Determine the molecular formula and heating value on dry basis and as received basis of the MSW using the following. So, this formula is given: high heating value in kilojoule megajoule per kg, that is equal to 0.3516 into carbon plus 1.16225 into hydrogen minus 0.1109 into oxygen plus 0.0628 into nitrogen plus 0.10465 into sulfur. So, here carbon, hydrogen, oxygen, nitrogen and sulfur are the percentage of these components in the biomass. So, if this waste is incinerated in fixed bed incinerator, what will be the composition of the flue gas if 20% excess air is supplied? So, this is the first questions. We have to determine the compositions of the flue gas if 20% excess air is supplied. We also have to determine the dry basis and as received basis heating value of this material. And the next part, if the ash of the above sample contains 0.3% K2O and 0.2% Na2O respectively, determine whether the waste will form slag in the furnace. So, we can divide it into three parts, that is, first is heating value determination, second part is determination of the composition of the gas streams, and third part whether there will be slagging in the reactor or not. So, here also we will take some basis, 100 gram of MSW. So, here it is given that carbon 35.5%, hydrogen 4.8%, oxygen 25%, nitrogen 0.40%, sulfur 0.15%, Cl 0.55%, moisture 26 and ash 7.6%. So, total is equal to 100%. So, out of 100 gram we will get carbon 35.5 gram, hydrogen 4.8 gram, oxygen 25, nitrogen 0.4, sulfur 0.15 gram, Cl 0.55 gram, moisture 26 gram and ash 7.6 gram. So, these are the mass out of 100 gram. We will convert it into moles, just like the previous problem, just divide it by molecular weight of carbon. So, 35.5 by 12, 2.958 moles. This is 4.8 divided by hydrogen. So, by 1, 4.8 moles, and 25 by 16, that is oxygen. So, we are getting 1.5625 moles, and then for nitrogen 0.4 by 14. So, 0.0286 moles, for sulfur 0.15 divided by 32. So, that is equal to 0.00471 moles, and then for chloride that is 0.55 divided by 35.5. So, it is 0.0155 moles, and moisture 26 divided by 18. So, 1.444 moles. This is for ash 7.6 divided by 56, that is 0.1356 moles. Now, up to this if we get, then we can represent the molecular formula or the presentation of the MSW is C 2.958, hydrogen 4.8, oxygen O 1.5625 like this, nitrogen will be 0.0286, sulfur will be 0.0047, and chloride will be 0.0155, ash will be 0.1357, and H2O moisture that is given 1.44. So, H2O will be 1.444. So, this is the molecular formula of the MSW. Now, the moisture that is 1.44 moles which is present in it, we can represent the same way, similar way, or this can also be presented like this, when H and O present in the moisture is considered here. So, that way also we can represent. So, H2O, this H plus O, 2H plus O. So, how many moles of H2O will be available here? The same number of moles of oxygen and 2 of that number of moles for hydrogen. So, hydrogen from moisture is equal to 2 into 1.444, that is 2.888 moles, and oxygen from moisture is equal to 1.44 moles. So, these two, this part can be replaced, H2O 1.444 can be replaced. In spite of that, the 2.888 can be added with 4.8, that is equal to H 7.688, and this oxygen 1.444 can be added with 1.5625. So, it is coming 3.0065. So, this is the way we can represent the MSW. So, if we want to solve the first part, this will be required to solve the second part. But if we want to solve the first part, we need only the percentage of carbon, percentage of hydrogen, percentage of oxygen, percentage of nitrogen, and percentage of sulfur, because this formula is given. These are the percentage of carbon, hydrogen, oxygen, nitrogen, and sulfur are required. So, we have two bases, one is as received basis and another is dry basis. So, on the basis of as received basis, we have 35.5 carbon, 4.8 hydrogen, 25 oxygen, 0.4 nitrogen, 0.15 sulfur, and 0.55 chlorine, and 7.6 ash. So, directly on as received basis, we will put the value of carbon as 35.5, value of hydrogen as 4.8, oxygen as 25, and for nitrogen 0.4, and for sulfur 0.15. So, this one, the 35.5, 4.8 for hydrogen, this is for 25 for oxygen, and 0.4 for nitrogen, and this is 0.15 for sulfur. So, we are getting 15.33 megajoule per kg. But if we want to find out this HSV on dry basis, we have to convert these values on dry basis first. So, dry basis means we have to remove the moisture first, and then the 35.5% will be converted to 47.97%, because this is 35.5 into 100 divided by 100 minus 26. Now, out of this 100 our basis, we are getting 26 moisture that will be removed. So, remaining will be 74 gram will be our material, dry material. So, that out of that 35.5 gram is carbon. So, 35.5 into 100 divided by 100 minus 26, that is 74 gram, that is equal to 47.97%. Similarly, for hydrogen this will be 4.8 into 100 divided by 100 minus 26, that is equal to 6.49%. Similarly, for oxygen we will be getting this way, that is 33.78 percentage, and the similar process nitrogen is equal to this one into 100 divided by 100 minus 26 equal to 0.54%. Similarly, sulfur is equal to 0.203%, chlorine is equal to 0.74% and acid is equal to 10.27%. So, these percents will be used now to calculate the HHV value, high heating value, and that will be on dry basis. So, 0.3516 into C, this C is equal to here 47.97, this H is equal to here 6.49, and then this oxygen is equal to here 33.78, and nitrogen is equal to 0.54 and sulfur is equal to 0.203. So, and we are getting 20.71 megajoule per kg. So, the first part is over, we have discussed. Now, for the second part, we have also calculated the molecular representation of the material. Now, we will consider the reactions. So, some combustion reactions is going on. We are assuming that Ca, Hb, Oc, Nd, Se, Clf and Sn. This is the presentation of the MSW, that is reacting with G moles of oxygen, and then it is giving us H mole of CO2, I mole of H2O, J mole of NO2, K mole of SO2, M mole of Cl2 and N mole of S. Now, so this is our molecular representation, that is C A is equal to 2.958, H is equal to 7.688, just we have discussed 7.688, and then next is equal to 3.0065, N equal to 0.0286, sulfur equal to 0.0047 and Cl equal to 0.0155 and S equal to 0.1357. Again component balance. So, left hand side and right hand side, if we do the carbon balance, so we can getting A is equal to H and that is equal to 2.958. So, that is equal to A equal to H equal to 2.958. Hydrogen balance, B left hand side, right hand side hydrogen is 2I. So, B is equal to 2I and B is equal to how much? 7.688. So, I is equal to B by 2, that is equal to 3.844. Then we are going for oxygen balance. So, oxygen C plus 2G. So, C plus 2G, that is equal to 2H, here we are getting 2H plus I, here it is coming I, and from this 2J plus 2J and here we are getting 2K. So, this is the oxygen balance from right and left hand side of this reaction. Then we will consider nitrogen balance. So, D is equal to J, D is equal to J and that is equal to we are getting 0.0286, and here also we have got the value of C from this stoichiometric from the molecular presentation of the material, that is C is equal to 3.0065. And then we will see the sulfur balance. So, E in the left hand side is equal to K and that is equal to 0.0047. Then we do chloride balance. So, F left hand side and right hand side is equal to 2m. So, F is equal to 2m, that is equal to 0.155. So, m is equal to F by 2, that is equal to 0.0155 divided by 2, that is 0.00775. Now, n is equal to S, so that will be 0.1357. So, now we have got the values of different coefficients here, but we need to get the value of G. So, we need to get the value of G, that will be our stoichiometric requirement of oxygen. So, G can be obtained from this formula, that is C plus 2J equal to 2H plus I plus 2J plus 2K. So, 2 into H we have got 2.958 here. So, 2 into 2.958 plus I is equal to 3.844 plus 2J is equal to 2 into 0.0286 plus 2K, so 2 into 0.0047. So, this is we are getting is equal to C plus 2Z. So, 2Z is equal to this minus C. So, 2Z is equal to 9.8266 minus this C, that is 3.0065. So, 3.0065, so it is coming 6.821. So, 2Z is equal to 6.821. So, G is equal to 6.821 divided by 2, that is equal to 3.41005. So, this is the value of G that is desirable. We are interested to know the value of G, and we are seeing here that is equal to 3.4100 moles. Now, as per the statement, 20% excess oxygen is supplied. So, this is the stoichiometric requirement 3.41005. If 20% excess oxygen is supplied, so oxygen supplied will be 1.2 into this much, 3.41005 into 1.2, that is equal to 4.09206 moles of oxygen. Again, we are assuming that 20% oxygen and 80% nitrogen in air. If this is the fact, and if we can assume this one, then obviously the nitrogen in the air will be 4 times of this. So, 4.09206 into 4. So, that is 16.36824 moles. So, this is the nitrogen which is present in the air, which is used for this combustion method. Now, what is the excess oxygen? Excess oxygen 20%. So, that will be this moles into 0.2. So, that is equal to 0.68201 mole. So, that will be the excess oxygen that will also be present in the flue gas. Then what will be the gas composition? Carbon dioxide is produced by say this H moles. So, that H value will be here 2.958 moles carbon dioxide. H2O will be how much? I. So, I value is equal to 3.844. So, it will be 3.844 moles. And what is NO2? NO2 value will be that is equal to J, and J is equal to 0.0286. So, we are getting 0.0286 moles. SO2 will be how much? K. So, K value is equal to 0.0047. So, we are getting here 0.0047 moles. And what is chloride? That is equal to M. So, chlorine, not chloride, chlorine. So, that will be M. So, M value is equal to 0.00775. So, that will be 0.00775 moles. And N2 is equal to how much? This is the N2. We are getting that how much N2 is present in the air. So, that is equal to 16.36824 moles. So, that is equal to total nitrogen present in it. And excess oxygen, this much is also present. So, it will come here, excess oxygen is equal to 0.68201 moles. So, these are the total moles present in the flue gas. So, that is equal to 23.89329 moles. So, now we can convert it in terms of percentage. So, CO2 will be 100 into 2.958 divided by 23.89329 moles. So, this is equal to 12.38%. Similarly, H2O will be 100 into 3.844 divided by 23.89329. So, that is equal to 16.09. Similarly, NO2 will be this divided by 23.89329, that is equal to 0.119, and SO2 will be determined like this 100 into 0.0047 divided by 23.89329. So, it is coming 0.019. Similarly, for chlorine, for chlorine this is 0.032, and for nitrogen this is 68.59 percentage, and excess oxygen, that is 0.68201 divided by 23.89329 into 100. So, that is equal to 2.85. So, this is the composition of the flue gas. Now, the third part, we have to find out whether there will be any slug formation or not. For this, we need to determine the slug index, and slug index we know that slugging index is equal to 0.1 into percentage of ash into percentage alkali in ash. So, this is the expression for slugging index in kg alkali per gigajoule. So, this is the unit of it. So, here if we put the value of percentage ash, that is 7.6% ash, as per the statement ash is 7.6%. So, 7.6 into percentage alkali, as per the statement K2O is 0.3%, Na2O in ash is equal to 0.2%. So, total alkali in ash is equal to 0.3 plus 0.2, that is equal to 0.5%. So, this is 0.5 into 7.6 into 0.1, that is equal to 0.38 kg alkali per gigajoule. Now, this value we have to find out where it is. As you know, we have already discussed in the previous module that if slugging index is within 0 to 0.17 kg alkali per gigajoule, then this is not slugging, no slug will form, but 0.17 to 0.34 kg per gigajoule there may be some slugging, probably slug, but if it is greater than 0.34 kg per gigajoule, that is virtual certainty of slugging. So, slugging will be taking place. So, in this case the value is 0.38, so more than the 0.34, so slugging will take place in this case. Now, problem number 3, the composition of flue gas dry basis from an incinerator is as follows: 12.3% CO2, 5.1% oxygen and the rest is nitrogen. From this data calculate the weight ratio of hydrogen to carbon in the waste, the percent carbon and hydrogen in the dry waste, the percent excess air used, the moles of exhaust gas discharged from the unit per kilogram dry waste burnt. So, these are the statements and we have to solve these 4 problems. So, A, B, C, D, 4 parts. So, for this what we need to do? We again need one basis. So, we are considering the basis is 100 moles of dry flue gas. So, flue gas is dry basis. Say we have one incinerator. So, we are getting some gas. So, this gas after cooling, so it is cooling, then we will get flue gas, dry. What is happening? It is basis as dry basis. So, when we will be making the flue gas in incinerator, that will be containing steam, H2O, which is H2O form here due to the combustion, that will be in vapor form. So, that will be reduced here. So, H2O will be separated. So, this will be dry gas. So, here the composition is given, the composition which is given here, that is CO2 and oxygen, excess amount of oxygen and oxygen. H2 is already separated here, some arrangement is made to separate the H2O. So, this is the situation. Now, the composition of the dry gas is given here. On this basis we have to find out the composition of gas here and what will be the H2O which is coming out from the incinerator also, that is the moles of exhaust gas discharged from the unit per kilogram dry waste burn. Other 3, the percent excess air, how much excess air is required, and the first 2, weight ratio of hydrogen to carbon in the waste and percentage carbon and hydrogen in the waste, very similar. Okay. So, the basis is say 100 moles dry flue gas, so 12.3% CO2 and oxygen is 5.1%. So, what are the rest? The rest will be here nitrogen. This nitrogen is coming from air. So, CO2, O2 and nitrogen is present in it. So, that will give us 100. So, 100 minus 12.3 minus 5.1, that is equal to 82.6% of nitrogen. So, what is the oxygen available with supplied air? So, 82.6 is nitrogen. So, into 21 divided by 79, we are assuming that 20 is to 21 is to 79 is the ratio of oxygen is to nitrogen in the air. So, this is our 22 moles of oxygen is available. Now oxygen consumed during combustion equal to how much? So 5.1% is available as excess oxygen. So the consumed is 22 minus 5.1, that is 16.9 moles, and what was the reaction? This C plus O2, that is CO2, and another was H2 plus O2, H2O we got. So that was the reaction. So from the flue gas composition, it is evident that the waste does not contain sulfur, chloride and nitrogen. Therefore 12.3 mole oxygen, the 12.3 moles of oxygen will be used by the carbon due to these reactions. 12.3 moles, this is 12.3 mole, it is present. So that was also, oxygen was also 12.3 mole. So oxygen consumed by hydrogen is 22 total oxygen, that was supplied 22 total oxygen minus used for carbon, that is 12.3, minus the amount of excess oxygen present. So that is 4.6 mole was used for the reaction or the combustion of hydrogen. So this reaction oxygen was this much, so that is equal to 4.6 mole. Therefore hydrogen present in waste is equal to 4.6 into 2. So here we are getting by stoichiometric, we are getting 2 moles 2H2. So that will be 4.6 into 2, 9.2 moles, and then weight of hydrogen in waste is equal to 9.2 into 2, that is 18.4 gram. So weight of carbon in waste equal to 12 into 12.3, that is equal to 147.6 gram. H2 carbon ratio in waste then how much? 18.4 divided by 147.6. So that is equal to 0.125 we are getting, and percentage in dry waste, that is 100 into this divided by this plus this. So we are getting 88.92%. Similarly for hydrogen, the percentage is this one and 11.02%, 08%, that is equal to 11.08%. So percent excess air applied equal to how much? We have 5.1 and reacted 22 minus 5.1. So that is equal to 5.1 divided by 16.9. So that is equal to 30.18%. H2O produced during combustion is equal to how much then? 2 into 4.6, that is equal to 9.2 moles, because this is our 2 reactions. So that is equal to 9.2 moles. So moles of exhaust gas per kg of waste, that is equal to 100 was our assumption for dry flue gas. Here we had 100 moles and now we are having here 100 plus the H2O. So that is equal to 9.2. So 100 plus 9.2 divided by 166, that is equal to 0.658 moles per gram of MSW, that is equal to 658 moles per kg of dry MSW. So now we have solved both the three parts of this problem, and with this we are at the end of this module. Thank you very much for your patience.